All right, this is just a reminder of what we discussed at the end of class yesterday. So when we have a projectile, we can determine the horizontal and vertical velocities of that projectile at any moment during its flight. And so the resultant velocity is going to be determined by adding the vectors for the horizontal velocity and the vertical velocity. Now we can represent a vector using an arrow, and the direction of the arrow is going to represent the direction of that component of that vector, and the length is going to be proportional to the magnitude of the vector. So if we're talking about velocity of a projectile, that projectile is going to have a vertical velocity, which we'll call v sub y, and it's going to have a horizontal velocity, which we'll call v sub x. Both of those are contributing to the overall motion, and the overall or the resultant velocity is going to be a combination of both the vertical and the horizontal velocities. Now, in order to add multiple vectors together, what we're going to do is we're going to place them head to tail. So the head of one vector is going to be placed with the tail of another. So instead of drawing like I drew here, where let's say a ball or whatever is a projectile has both a horizontal and a vertical velocity, what I'm going to do is I'm going to move the y component so that the head of the x component is touching the tail of the y component. So that's going to look like this. So that's my x. And my y, I'm going to put the tail of the y with the head of the x. Now, the advantage of that is that this allows us to calculate the resultant velocity, which is just going to be drawing from our origin, which would be right here, so where we're measuring from, to the tip of the last vector. In this case, it's our y velocity. So that's going to be our resultant velocity that I'm going to call VR. What you'll notice is that this makes a right triangle. So now we can use all of the rules and theorems that you learned maybe in geometry class in order to look at the relationship between the resultant velocity, in this case, and the x and the y components of the vector. So if I wanted to calculate the resultant velocity and I knew x and y, I could use Pythagorean theorem. So in this case, the resultant velocity squared is equal to vx squared plus vy squared. Remember, that's a squared plus b squared equals c squared. So if I wanted to calculate the resultant velocity in this case, or the resultant vector, I can just take the square root of vx squared plus vy squared. This would give me the magnitude of the resultant vector. But remember, just as important as the magnitude is the direction. So we could also calculate in which direction is this pointing. In order to do that, we want to be precise. And so we can actually calculate this angle relative to the horizontal plane. This is our horizontal plane. We can calculate that angle using trigonometry. So if you remember, we have SOHCAHTOA. Again, I'm assuming this is a review, but sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if I know the y and the x components of velocity, I can easily calculate this angle. We can calculate it using tangent because it would be opposite over adjacent. So I can say tangent of theta, angles are represented with the Greek letter theta, is equal to Vy over Vx. So if I want to calculate the angle, I can do the inverse tangent of Vy over Vx is equal to theta. The way that you would do that in your graphing calculator is you would click second tan and then do your Vy over Vx values. The way that we would then represent our resultant vector would be whatever we get for our magnitude, and then we would describe the angle relative to the horizontal. So let me show you an example really quick. Okay, here's an example problem that I just made up. So here we have a ball thrown with a horizontal trajectory from the top of a building, and it has a velocity of 25.1 meters per second. So part A is asking how far will the ball travel in the horizontal direction if the building is 20 meters tall. So let's draw a quick picture. Here's my building. Here's my ball. And it's being thrown. And it's going to hit the ground at some point. Okay, so I know my building is 20 meters tall. And so my initial position in the y direction, again, where I start in the vertical direction, is 20 meters. And then I know the ground then would have to be 0. I'm going to start my horizontal measurement at the edge of the building. So I'm going to call my initial position where I start from horizontally is 0. And then where the ball hits the ground in the horizontal direction, I don't know that yet. That's what I need to calculate. There's some other information that's given in this problem. So I know that I have a perfectly horizontal trajectory. So the ball isn't moving up or down at the beginning. So I know that my initial velocity in the y direction is 0. And I know that the ball has a velocity in the x direction of 25.1 meters per second, because that's given to me in the problem. I know that in these problems, the acceleration in the x direction is 0 because the velocity isn't changing in the x direction. It continues to go at the same velocity the whole time. And the acceleration in the y direction is negative 9.81 meters per second squared. That's just acceleration due to gravity. One last thing, or one last component that we don't know, is how long does it take for the ball to go from the top of the building to the ground. So that's the first thing that we're going to have to figure out. And once we know that, we can figure out how far the ball goes in the x direction. To figure out how long it takes for the ball to fall, we're going to use this equation. We'll be able to fill in every variable except for time. So I know that y, my vertical position of interest here, is going to be 0 because we're interested when it hits the ground. 1/2 acceleration is negative 9.81 in the y direction, and then we don't know what time is. For this next component or term, my initial velocity in the y direction is 0. So 0 times time is 0. So this term is just going to go away because it's going to end up being 0. And then lastly, I have my initial y position. So where we start in the vertical plane is at 20. So I'll say plus 20. So now all we have to do is solve algebraically for t. So I'll subtract 20 from both sides. This ends up being negative 4.905 t squared. I'm going to divide 20 by 4.905. And I get 4.08. So t squared equals 4.08. And so the time it takes to fall 20 meters is going to be the square root of that, which is 2.02 seconds. Now I can use that to figure out how far is the ball flying in the horizontal direction, because I know how long it's going to be in flight until it hits the ground. So we'll move over here, and I'm going to use the same equation just in the x-plane. So x equals 1/2 at squared plus initial velocity in the x direction times time plus initial x position. Now, I don't know how far it's going to fly. That's our position of interest. So we'll keep that as x. I know that my acceleration in the x direction is 0. So I'm going to multiply this whole term by 0 because 0 is going to be filled in for a. So this whole term, 1/2 at squared, is going to be ignored because it's 0. In addition, my initial x position we defined as 0. So this term at the end is also going to be ignored. So the only variables we have to fill in are initial velocity in the x direction and time. So my initial velocity in the x direction is 25.1. And my time we just calculated is 2.02 seconds. So the distance that it's going to fly in the x direction is just 25.1 times 2.02, which gives me 50.7 meters. So that's going to be the answer to A, 50.7 meters. Okay. So part B is asking, what is the magnitude and direction of the velocity vector for the ball when it reaches a height of 10 meters? Okay, so instead of calling our y position of interest 0, now my y position of interest is 10. So I'm going to say y is equal to 10, which is about halfway down the building. And we know at a height of 10, we're probably going to be somewhere out here. So there is going to be a vertical and horizontal component to velocity. So the first thing we need to do is figure out how long is it going to take to get from our initial position of 20 to our position of interest, which is 10. Again, we're going to use my favorite equation, which looks like this, and we'll use it in the y direction. And so let's remember some of these things. So I know that my initial velocity in the y direction is 0, and my initial velocity in the x direction is given to us as 25.1. I know that acceleration in the y direction is negative 9.81, and in the x direction, it's 0. Now, what I don't know is how long will it take for the ball to get to a height of 10 meters. That's what we're going to figure out using this equation. Again, remember, initial velocity in the y direction is 0, so this whole term is going to be ignored because it's going to end up being 0. So we can fill this in as, now I know y is 10 is equal to 1/2 and then negative 9.81 times t squared. I don't know how long it's going to take to get to the 10 meter point. This term is 0, and my initial position is 20. So now we can solve for t algebraically. So I'm going to subtract 20 from both sides to start. So now I have negative 10 is equal to negative 4.905 times t squared. I can do 10 divided by negative 4.905 to get 2.04. So t squared equals 2.04. I'll take the square root of that. And I get 1.43. So it'll take 1.43 seconds to get to a height of 10 meters. Now I need to find out what is the velocity of the ball in the y direction at a time of 1.43 seconds. So now I'm going to use my second favorite equation. So my velocity in the y direction is equal to at plus initial velocity in the y direction. Initial velocity in the y direction, again, is 0. So this term is going to be ignored. So then I can just calculate my y velocity as negative 9.81 times time, which we just determined was 1.43. So my y velocity is negative 14.0 meters per second. Okay, the x velocity was given to us, and remember, because the acceleration in the x direction is 0, the velocity in the x direction throughout the entire time of flight is going to be 25.1. It's not going to change. So now what we can do is draw out our vector diagram showing both the x and the y components of velocity. So I know that my x component is going to be 25.1, and we just determined that our y component is negative 14.0. So let's draw this out. So I'll draw my x first, and we'll call that 25.1. And I'll draw my origin in here. And then my y component is 14.0. So because my y component is negative, I'm drawing it in the downward direction. And you can think intuitively, if you throw a ball off a building, the vertical component of velocity is going to be in the downward direction. Next thing I'm going to do is I want to draw my vectors head to tail. So I'm going to slide my y component over. So this will be 25. And now I want to draw this head to tail. So this is 14. And then I want to connect the origin to the tip of the last vector, which is down here. So this is my resultant velocity vector. All right? So remember I said we can calculate the magnitude of the resultant velocity using the Pythagorean theorem. So I know that VR squared is equal to 25 squared plus 14 squared, because this is a right triangle. So in order to calculate the resultant velocity magnitude, I just need to take the square root of 25 squared plus 14 squared. So I'm going to type that into my calculator really fast. Oops. And so I got 28.7 meters per second. Okay. I also need to describe the direction. So we're going to call this angle theta. And I can determine the angle relative to the horizontal by determining what theta is. So I can do that using the tangent function. So I know tangent theta is opposite over adjacent. So that's going to be 14 over 25. In order to solve for theta, I can do the inverse tangent of 14 over 25 is equal to theta. So I'm going to, in my calculator, do second tangent, 14 divided by 25. And I end up getting 29.2 degrees. So the way that we would write our final answer for our resultant velocity vector is we would say our vector is 28.7 meters per second at 29.2 degrees below the horizontal. So that would be it.